Hello students, welcome to Inside Physics. Today we are going to discuss about Bernoulli Principle. Bernoulli Principle is related to fluid flow. So this fluid flow, when we are studying some flow of the fluid, it is also called fluid dynamics. So some textbooks say it is mechanical properties of fluids. So mechanical properties here are nothing but the velocity, the acceleration and the flow which is observed through the pipe, which is having a variable cross sectional area. Now what does the Bernoulli principle says? So he is a Swiss scientist. The principle was proposed in 1738 by Daniel Bernoulli. So according to him, there is a relation between pressure and the varying kinetic energy and the potential energy when a incompressible liquid is flowing through a pipe of varying cross sectional area. If you observe this pipe here, in which we are actually moving a fluid which is incompressible, that means we are not considering the elastic energy of the fluid, and it is a steady flow. Steady means non-turbulent flow. Here we observe that the fluid is entering into this cross-sectional area and it is moving through this pipe. You can observe the cross-sectional area increasing while the liquid is moving from here to here. So while moving to this area to that end, the height of the liquid is also changing. You can observe the height of the liquid here is H1 and here is H2, and we also observe that A1 is the area of cross section of this particular opening and A2 is the area of cross section of this opening at the other end through which the liquid will come out. Here we are considering the liquid entering here, and in a small time delta t, the liquid is flowing through B to C. Okay, at the same time, in the time interval delta t, here the liquid will flow from D to E. So B to C is very small distance. We can consider the area of cross section from B to C almost same. That is why we consider this B to C is very small distance. So what happens actually here, when the liquid is moving, it must have some force to be pushed through the pipe. The force is generated from the surrounding liquid of this flow. When this liquid is flowing, the surrounding liquid is nothing but the liquid which is besides this, and this has a force beyond which is not shown here. The surrounding liquid will push the liquid, and thus that force actually creates the acceleration through the pipe. So the variation of velocity through the pipe is according to principle of continuity. Whenever there is a less cross section area, small cross section area, the velocity will be more. So to maintain the equation of continuity, the velocity is varying through the pipe because the cross sectional area is also varying. So here how to proceed here? We use the law of conservation of energy to relate the relation between pressure, kinetic energy and potential energy. According to Bernoulli principle, the total sum of the pressure, kinetic energy and potential energy is constant throughout this pipe. That is what the Bernoulli principle says. Now for that we use the law of conservation of energy, because there is an energy concept. The potential energy is varying with the height, and the kinetic energy of the liquid is also varying with the velocity change, and the pressure inside the tube may be also varying with different points. If you consider the pressure here and the pressure here, that may be varying. So here the work done on the liquid, here we consider the work done on the liquid, because we are considering the law of conservation of energy, we know that work done is nothing but force into displacement. Okay, force is nothing but related to pressure. We can write pressure is equal to force per unit area. We know these relations. So here, if you consider the force from this, it will be like pressure into area of cross section. So we replace force here in place of, to get the work done relation in terms of pressure and area of cross section, and S is the displacement of the liquid. So in this regard, the work done on the liquid here, so work must be done because of some force. The force exerted by the side by liquid, the surrounding liquid will do the work on the liquid here, that is considered as W1. So here the pressure is P1 according to this formula, and the area of cross section is A1 at the point B. So the distance moved by the liquid in an infinitesimal small time delta t from B to C. So the distance moved, we know distance moved is equal to velocity into time. That is already we know from the kinematics. This relation is applied here. So the displacement of the liquid from B to C can be taken as in this way. So if you observe this, this is pressure into area of cross section into displacement of the liquid gives volume of the area. This volume is done by A1 into displacement. So this can be written as delta V. Okay. Again, the work done by the fluid here, because there is a work done and the fluid is pushed, and the work done by the fluid here is written as W2 is equal to minus P2 delta V. We can use the same principle and we can write it as minus P2 delta V, because the pressure at other end at E is P2. This is work done on the fluid, this is work done by the fluid. That's why we got minus here. If you convert this into work done on the fluid, we can get this relation as P2 delta V or P2 delta V. So the work done on the liquid from these two relations can be written as the total work done on the liquid can be written as P1 delta V minus P2 delta V. So this can be written as P1 minus P2 into delta V. So this is the work done. We know that from work energy theorem, the work done is nothing but change in kinetic energy or change in potential energy. Sometimes the both changes in kinetic energy and potential energy will be equivalent to the work done. According to that principle, we also must calculate the change in kinetic energy. So if the velocity is V1 here and the velocity is V2, what we require? The change in kinetic energy delta K. Change in kinetic energy delta K is equal to half m V2 square minus half m V1 square. Okay. So here m is the mass of the liquid. M is nothing but mass of the liquid. So how to get the mass of the liquid? Mass is nothing but, we know that the relation density is equal to mass per unit volume. So mass is equal to density of the liquid and into volume of the liquid. Here the same way we can write here half m is nothing but density of the liquid is considered as rho, and volume here velocity, volume is delta V, and this is mass of the liquid, and V2 square minus half into rho delta V into V1 square. Okay. So here what we can take the common factor as rho delta V can be taken as the common factor, and this relation will become V2 square minus V1 square. This is the change in kinetic energy. So next, what is the change in potential energy? Potential energy means we know that from kinematics that change in potential energy must be written as mgh. So initial final potential energy minus initial potential energy. So this can be written as like this. So there is a height variation, so there must be potential energy variation also there. So in this regard, what we will write for the change in potential energy? So delta U, where U is considered as potential energy, must be mg h2 minus mg h1. So we know that here mass is nothing but density into volume. Already we have written that into g h2 minus rho delta V into GH1. If you take a common factor of these two, rho delta V into GH2 minus H1, this is nothing but change in potential energy. Okay. So here we must, according to the work energy theorem, the work done, what is the work done here? We already calculated P1 minus P2 into delta V is equal to change in kinetic energy plus change in potential energy. So in this way we can write it as half rho delta V V2 square minus V1 square plus rho delta V Z. Z is nothing but acceleration due to gravity. Where there is a height concept, we must consider the gravity. So the gravitational force always pulls the liquid downwards. So that is the force acting downwards. Here we must have the difference in height, then only there will be a change in potential energy. So here if you divide the left hand side and right hand side with this value delta V, that means volume. So we must get here P1 minus P2 is equal to plus rho Z. This is not P, this is rho Z into H2 minus H1. Okay. So here by exchanging the terms we can write, see, from this relation we can take it as equation 1. From this equation 1 we can exchange the terms and we can equate the relation in this form. So I will write here. See, this half rho v1 square is brought to the left side, and rho g h1, this term rho g h1 is brought to the left side. So from this relation, what we can write? P1 plus half rho v1 square plus rho g h1 is equal to P2. See, this P2 is brought to the right side. P2 is brought to the right side. So I can write P2 plus half rho V2 square plus rho G H2. So this is the relation we got. If you observe this relation, you can understand one thing. So the energy throughout the movement of the liquid is also constant at any place, and this change in potential energy and kinetic energy is also added with the pressure. So by observing this equation, we can say throughout the motion of the liquid in a pipe or in a tube with varying cross sectional area, we can write that pressure plus kinetic energy plus potential energy is equal to constant. So this is what the Bernoulli principle says. We can take it as any constant like K or C, whatever it may be, but this is the final observation. Pressure at any point, the kinetic energy of the liquid at any point throughout the tube, and the potential energy is constant. So this is a simple relation observed by the Bernoulli, and we can have some good principles or problems solved with this relation. But here there is a drawback in this principle also. So there are some constraints in which we cannot apply the Bernoulli principle. Here, when we are considering the law of conservation of energy, we have ignored the frictional force between the layers of the liquid. Whenever a liquid flows, it flows in layers. So the frictional force, or in general we call it as the viscous force or viscosity, is not considered here. So we consider the liquid flowing is a non-viscous liquid because we are not considering the viscosity. So viscosity is not considered. Okay, so we consider the liquid is non-viscous and we will proceed. The second one, the liquid we have considered is incompressible. That means I have also ignored the compressibility, that means elastic energy of the liquid. So the elastic energy may be also varying, so that we cannot apply this principle to that particular elastic energy. So here that is also ignored. So elastic energy, that means the liquid must be incompressible. Okay. So the third one here, we cannot apply Bernoulli principle to turbulent flows. Turbulent means it is non-steady flow. We can only apply the Bernoulli principle to steady flows or streamlined flows. Why? Because in a turbulent flow, the pressure and area of cross section and velocity will be varying from point to point and time to time. So here there are the drawbacks. So here the liquid considered is a steady fluid. It is considered as a steady fluid, that means non-turbulent. Okay, so these are the drawbacks of Bernoulli principle, and this is the relation where we can call it as the famous Bernoulli's principle. That's the end of this video. We will be coming up with some more interesting topics in fluid mechanics. Thank you.